Okay, in this video of what's in the bleakin beaker, we're going to look at acetic acid, HC2H3O2, and in this beaker, that's a weak acid. But in this beaker, we've also added some salt, sodium acetate, NaC2H3O2. And we know that the weak acid will remain predominantly as the molecule, but what happens with our salt? If our salt is soluble, it 100% ionizes, so we don't have sodium acetate in the beaker. We have acetate ion, and floating around, we have sodium ion. Now we already know sodium ion in solution is a spectator. So the two things that interest us in this bleakin beaker are the weak acid and its conjugate base, which came from a salt. And when you have the acid, the weak acid, and its conjugate base, usually from a salt dissociation, then you have what is termed as a common ion. Problem. Okay? It is still based off of the equilibrium for a weak acid. So we are still going to say HA plus water. The acid donates the proton, you get the hydronium ion, and the conjugate base of the weak acid. So this is still my equilibrium. I don't really worry about the conjugate bases coming from the salt just yet. That doesn't dictate what equilibrium I write. The weak acid is going to dictate the equilibrium I choose of my 4. So you can either do HA or you can write out acetic acid. I choose to do acetic acid this time. So HC2H3O2, only to help you see the common ion a little bit better. So that would be the acetate would be left over. There you go. So this is R. We're still going to start with our rice table. Initially, I need to give you a concentration of both of these. So I'm going to tell you that the initial concentration of the acetic acid is 0.25 molar, and that the salt concentration is 1/10 molar. Now I could start you in grams and you convert to moles and then divide by the volume in the beaker and get molarity, but just wanted to make it shorter. So here we go. We've got 1/10 molar salt. Well, what happens when the salt dissociates? It forms sodium ions and acetate ions in a 1-to-1 mole ratio. So if this is 1/10 molar for the salt, this is 1/10 molar for sodium, but it's a spectator, so I don't care. But I do care about the concentration of that acetate ion. Why? Because here it is. We've got to look. Right there. There's the acetate ion. So it's not going to be 0 initially the way it is in our other rice tables. It is actually going to start out at 0.10 molar, and the acetic acid is 0.25 molar. Water, we still don't care about, and we don't have any of that to begin with. So the big difference when you have the common ion problem is right here. You are going to have an initial amount, not only of the weak acid, but of its conjugate from the salt. Change. Some of this is going to ionize. How much? We call it X. Then we form X, we form X. And then at equilibrium, remember E is equilibrium, 0.25 minus X, X, and this time, look, it's 1/10 plus X. Oh my gosh, okay. So in the common ion problem, then having some of this ion initially present is going to retard the dissociation or ionization of the weak acid. And so X is definitely going to be less than 5%. And so if it's a common ion problem where you have some initially of the conjugate of the weak, then you're always going to get to neglect this X without doing the test. So here you go. So here you have K. This is a weak acid, so you need Ka equals concentration of products to their coefficient over the concentration of the weak acid. Ka for acetic acid is just a coincidence, is the same as ammonia. So here we go. So we end up with 1.8 E minus 5 equals X times 0.10 plus X, but we know we get to ignore that X, and 0.25 minus X is essentially 0.25. So the common ion problems are much more easy to solve mathematically. And when we do that, we end up getting a X value of, I didn't do it, so I'm going to do it now. .8 times 10 to the minus 5 times 0.25 divided by 1/10, and we get 4.5. 4.5 times 10 to the minus 5, and that's a concentration, that's molarity. What did we define X to be? X is hydronium ion concentration. So if this question asked me for hydronium ion concentration, I'm done. If it asked me for the pH, I need to take the negative log of that number and round it to 2 sig figs, and I get 4.35. The pH is 4.35. 2 sig figs, remember pH and pOH, only count the digits behind. So if it asks me for hydronium ion, I'm done. If it asks me for the pH, I'm done.